question says that in which of the following example of motion can the body be considered approximately a point object? So this question is talking about the approximation of body in motion to be that of a point object in motion. So let's look at the first option, the railway carriage moving without jerks between two stations. So first of all, we make our concept clear about the assumption about the point object approximation. So if the size of a body is too small as compared to the distance it travels in a reasonable amount of time, then we can assume that the body is a point object. The body in motion is a point object. So considering our first example, the railway carriage moving without jerks between two stations. So here the distance between two stations may be 1000 kilometers, maybe 100 kilometers, maybe tens of kilometers, but the railway carriage is of range 10 to 15 meters, which is too small as compared to the distance it travels between a station. So the approximation of the moving object, that is the railway carriage, which is moving without jerks between two stations, can be considered as a point object motion. So this is true in this case. Now moving on to the next option, we have a monkey sitting on top of a man cycling smoothly on circular track. So here the circular track is there and a man is cycling in that circular track. So if we observe the moving object here, that is the man cycling and a monkey sitting on top of the man, so the length of this object, moving object, is in the range of 1.5 meters to 1 meter. We can say that we can also assume that the circular track would be about 250 meters in length, or some in this range the railway cycling track generally exists. So as compared to the distance it will travel in some time, the length of the object is too small. So the assumption of point object in motion is true here also. Moving on to the next option, we have a spinning cricket ball that turns sharply on hitting the ground. So here it is talking about a cricket ball that is spinning, it is touching the ground and it changes the direction. So in this case, point object can't be considered because turning of the ball is not a point phenomena, at least it is a surface phenomena, which accounts for angular motion and many other variables. That is why it is too complex for the point object to resolve this problem. So this assumption would not be fitting in this case, so we can say it is false. And the fourth option, we have a tumbling beaker that has slipped off the edge of a table. So generally the height of a table is in the range of 1 meter, or it is less than 1 meter, or maybe hardly 1.2 meters. And beaker is of range of maybe 30 centimeter in diameter. So the falling of the beaker in this case can't be considered as a point object in motion, because the dimension of beaker is not much smaller than the distance it will travel in a very short interval of time actually. So the point object can't be approximated as the tumbling beaker. So the option will be false over here also. Thank you. In this question, we have the position time graph of two children A and B returning from their school O to their homes P and Q respectively are shown in figure 2.9. So this is the figure. Choose the correct entries in the bracket below. So this plot represents the graph of two children A and B who is returning from school to their home. School is the point O here, and home is represented on the position axis by points P and Q. Now A's home is P and B's home is Q. It is evident from this plot also. So the first question asks which candidate lives closer to the school. So in the position time plot, we can see that point P is nearer to school as compared to point Q. So the candidate corresponding to point P is A. So A lives closer than B to school. In the second option, we have which candidate starts from school earlier than which other candidate. So starting earlier, we see at the time scale, we see at the time axis. So here it is quite evident that candidate A starts early as compared to candidate B. So candidate B starts at this much delay after the candidate A has already started the journey from school to their home. So A starts early than B. Now third question, we have which candidate walks faster than the other one. So position time plot, the slope of position time plot gives us the velocity. So the tangent of a straight line is going to be the line itself, and we see here that as greater the tangent, the angle subtended by the tangent B, the slope would be bigger. So here B is making a bigger angle as compared to A, so velocity of B is going to be bigger than that of the velocity of A. So B walks faster than A. Now in fourth option, we have A and B reaches home at same or different time. Clearly it is evident that A reaches later than B. B reaches quickly, so at different time. Now in fifth option, we have A or B overtakes B or A on the road once or twice. So clearly their intersection point is just one, so they intersect only once. And who overtakes who on the road? It means which candidate passes the other candidate and goes further quickly. So at any time point after their point of intersection, if we plot a vertical, we see that the position of B is greater than that of A, so B will overtake A on the road once. The question says a woman starts from her home at 9 a.m., walks with a speed of 5 km per hour on a straight road up to her office 2.5 km away, stays at the office up to 5 p.m. and returns home by an auto with speed of 25 km per hour. Choose suitable scales and plot the xt graph. So we have to plot the position time graph of this woman whose distance from her office to home is 2.5 km, and she travels at the speed of 5 km per hour in the morning at 9 a.m. and she returns back with a speed of 25 km per hour at 5 p.m. So we have to plot the position time plot of this woman. So let's assume that this point represents the starting, or this point represents the starting point, that is 9 a.m. How much time she took to reach her office from home can be found out with this time equals to speed upon distance, that is 2.5 distance 2.5 upon 5 km per hour, that would be 0.5 hour. It means 30 minutes. So by 9:30 she would be reaching her office, which is 2.5 kilometer away, and she's traveling with a constant speed. So this is going to be a straight line, and she stays at her office till 5 p.m. So the position doesn't change till this 5 p.m. Now she again travel back to her home at a speed of 25 km per hour, and while traveling home she covers the same distance, that is 2.5 km. So again time would be equal to distance divided by velocity, 2.5 km divided by 25 km per hour, we have 0.1 hour, and that would be equal to 6 minutes. So at 5:06 p.m. she has reached her home back. So this would be the rough sketch of her position time plot from her home to her office from 9 p.m. to 5:06 p.m. Thank you. The question says, a drunkard walking in a narrow lane takes 5 steps forward and 3 steps backward, followed again by 5 steps forward and 3 steps backward, and so on. Each step is 1 meter long and requires 1 second. Plot the xt graph of this motion, determining graphically and otherwise how long the drunkard takes to fall in a pit of 13 meters away from the start. So basically there is a case of a drunkard who is traveling on a narrow lane, and he takes 5 steps forward and 3 steps backward, and he repeats this pattern until he falls in a pit that is 13 meters away from his starting point. So let us talk about his one cycle, that is 5 step forward and 3 step backward. So the step is 1 meter long, and the time required in each step is 1 second. So let's plot the graph. So let's assume this is the starting point of time. So we are plotting here one cycle. So let's assume that he travels 1 meter in one step, 1 second, 2 second, 3 second, 4 second, and 5th second. Now he's gonna return back 3 steps. So each of this step is of 1 second. So he will be returning back like this, 1, 2, and 3. So this is the 0th position, and this is the 5 meter position. And when he returns 3 steps back, it means he travels 3 meter back, and this represents 2 so this will represent 2 meters. So net displacement he would be having in one cycle is of 2 meter. So this would be one cycle that he is making while traveling on the narrow lane. So let us now plot his xt plot. So this would be the starting point at reference time 0, and he takes 5 steps forward, then 3 steps backward. So now he is at 2 meter, and he is at 8 second. Again he will take 5 meter forward and 3 meter backward, and he will be at 16 second, and this distance would be 4 meter. Again he will be taking 5 meter forward, 3 meter backward, and he would be at 24 second, and he would be at 6 meter. Now again he travels 11 meter, so the forward step is going to be 6 plus 5 is 11 meter, and then again he will depreciate it to 8 meters, and the time would be 32 seconds. Now again he will be moving forward, and this time he would be going 5 meter ahead from 8 meter, so he'd be traveling this 13 meter, and at 13 meter the time would be 32 plus 32 seconds plus 5 seconds, that is equal to 37 seconds. And at 13 meter he will be meeting the pit, and he will fall in that pit, and he will end his journey. So the time that will take to fall in the pit is going to be 37 seconds. Thank you. The question talks about a car moving along a straight highway with a speed of 126 km per hour is brought to a stop within the distance of 200 meter. So we need to find out the retardation or the negative acceleration that is applied by the brake of the car, and how long, what is the time duration that is taken by the car to be at full stop. So let us pictorially represent this case. The car C is moving at a speed of 126 km per hour. Driver applies brake and it stops at 200 meter. We have to find out A, and we have to find out time t it requires to stop. So first of all we will convert it to the distance to same scale, and it will be convenient for us to go for meter per second as the distance is in meter. So converting this value of velocity to meter per second, we have 126 into 1000 meter divided by 3600 seconds, that would yield us 35 meter per second. Now we know the relation of v square is equals to u square plus 2as. So this will give us the unknown acceleration, because this is only unknown in this equation. Final velocity is obviously 0 and initial velocity is 35 meter per second, plus 2 into acceleration into distance, that is 200 meter. So acceleration would be equals to 1225 divided by 400, and that would give us 3.06 meter per second square, negative of 3.06 meter per second square. Now we have to find out time that it takes to come at full stop. So we also know the second relation, that is v equals to u plus at. So v 0, here u is 35 meter per second, plus acceleration is negative of 3.06 multiplied by time. So time would be 35 divided by 3.06, and that would give us 11.4 seconds. So 11.4 seconds is required for the car to come at full stop, which was traveling initially at 35 meter per second, and the brake applied a deceleration of 3.06 meter per second square, thus making it stop 200 meter farther. Thank you. Question says that the player throws the ball upwards with an initial speed of 29.4 meter per second. Now we have to find out the direction of acceleration during the upward motion of the ball. So let us assume that this is the ground level and the player is here, and it projects the ball vertically up at a speed of 29.4 meter per second. Now when the ball is going upward, the gravitational force is acting downwards, therefore the acceleration is going to be acting downwards while the ball is moving, or it is in the air. Even though the ball is moving down, the acceleration is going to be in the same direction, that is in the downward direction. So the direction of acceleration during the upward motion of the ball would be downwards. Vertically downwards. Now the second question says that what are the velocity and acceleration of the ball at the highest point of its motion. So clearly at highest point, the ball will reach at the highest point when it has exhausted its velocity. Then velocity is going to be 0 at the highest point, and acceleration would be still acting with constant value, and that is g, that is 9.8 meter per second square. So acceleration is going to be same while the ball was moving upwards and at the highest point also. So it is going to be 9.8 meter per second square downward, in the downward direction. Now in third question we have choose the x equal to 0 meter and t equals to 0 second in the to be the location and time of the ball at its highest point. Vertically downward direction to be the direction positive of the x-axis, and give the signs of position, velocity and acceleration of the ball during the upward and downward motion. So basically this question is saying that choose this axis to be the origin, that is x equal to 0, time equal to 0 at the highest point where the ball reaches, to be the starting point, and the downward direction to be positive x-axis. So now we have to find out the signs of position throughout the travel. So clearly if this direction is positive, then the ball will always be in positive position, because at highest point the ball doesn't go beyond the highest point, so it is always going to be in the positive direction of the axis. So the position vector is also always going to be positive. Velocity, when the body is moving upward, then it will have a direction in the negative direction of the x-axis, thereby making it negative when going upward. And when the ball is moving downwards, then it is going to be positive because it is directing in the positive direction of the x-axis. So upward motion velocity is negative, and acceleration for the whole journey is going to be in the positive direction because it is always acting downwards and the downward axis is chosen to be positive. So acceleration will be positive in upward motion as well as downward motion, whereas velocity will be positive in downward motion, and acceleration is always going to be positive. This is for the third, or C. Now the fourth, or the D option, says that to what height does the ball rise and how long does the ball return to the player's hand. So we have to find out displacement, the distance carried, traveled by the ball in the whole journey of moving up and down, and the time that it took. So let's first talk about the time. So again we are choosing this as our origin, the point on the ground where the ball where the player is. So we see in the whole direction in the whole distance traveled by the ball, we see displacement is going to be 0. So we can say that in this relation s equals to ut plus half at square. Even though the ball has been thrown up, then it reaches downwards and it touches the same position where it started from. So displacement is going to be 0 and u is going to be 29.4 meter per second into time we don't know, that is unknown, plus half acceleration is going to be in the downward direction, so we have chosen it to be negative of 9.8 meter per second square multiplied by time square. So taking time as common, we have 29.4 minus 9.8 by 2 meter per second square time. So this will give us a solution of first time t equals to 0 and the next time t equals to approximately 5.9 or 6 seconds. So now we know that since at time t equals to 0 the ball was at same position where it started, so this is the redundant solution. So we will just ignore that and we will focus on this time, that is at time t equal to 6 seconds the ball is at the point where it started. Now the second part of the question was, what is the distance traveled by the ball? So we also know the other relation that relates velocity and displacement with acceleration as v square equals to u square plus 2as. So considering the upward motion, final velocity is going to be 0 equals to initial velocity was 29.4 meter per second, so putting a square, plus 2 multiplied by minus 9.8 meter per second square multiplied by displacement, that is s. So s is going to be equal to 29.4 multiplied by 29.4 divided by 2 multiplied by 9.8. That would give us 44.1 meter. Thank you. The question says that read the statement below carefully and state with reasons and examples if this is true or false. A particle in one-dimensional motion with zero speed at any instant may have non-zero acceleration at that instant. So let us consider a case here where a ball is being thrown upwards by a player, and we all know that it stops somewhere where it reaches the highest point. Its position doesn't increase any further. It means v equals to 0 at that instant. Still, now it will go downward, but still we have an acceleration acting downwards, that is a gravitation due to gravitational force, which is 9.8 meter per second square. So this statement with zero speed at any instant may have non-zero acceleration is true, as we have seen in this case. Now the second question is, with zero speed may have non-zero velocity. So speed is nothing but the magnitude of velocity vector, and with zero magnitude we can't have velocity either, so this is a false statement. Now in third question we have, with constant speed must have zero acceleration. This statement is true, but since this is a one-dimensional motion case, this statement has to be true, because there may be a second case where a ball, in an ideal case, let us say that a ball hits a particle hits a wall and rebounds with the same velocity in opposite direction. Here speed is going to be same, but the velocity direction has changed in a very short interval of time, which will result in a very high acceleration value, and that is going to be very unphysical. So we can say that the speed still was constant, but acceleration existed there. But this unphysical acceleration can be neglected here, and this option is true for one-dimensional case also. Now in fourth option we have, with positive value of acceleration must be speeding up. So since acceleration is a vector quantity, we have a direction which depend upon axis. Let us assume that ball throwing case up in the case of like B in like A, when a player throws the ball upwards, and we assume that the positive axis is downward axis, and so when this ball is thrown upward and it rebound and it then returns to downward direction, during the whole journey the acceleration was acting downward, and since downward direction is positive, so acceleration is going to be positive, even though the velocity still decreased when the ball moved upward. So this statement is false, claiming that velocity always increases when acceleration is positive. Thank you. The question says that a ball is dropped from a height of 90 meter on a floor. At each collision with the floor, the ball loses 1/10 of its speed. Plot the speed time graph of its motion between time t equals to 0 to t equals to 12 seconds. So let us assume that this is the case. A ball is being dropped from here, which is 90 meter high. Once it is dropped, it rebounds with a velocity of 0.9 of the initial velocity, and again it is dropped, and again it rebounds to 0.9% of its last 0.9 times its last velocity. So we have to plot the speed time plot of this scenario. Now in a speed time plot, what we need to know is the speed it reaches when it goes to the ground, and the time that it takes for reaching the ground. So final velocity at the ground in the first instance can be calculated by relation v square equals u square plus 2as, where v stands for final velocity, u stands for initial velocity, a is the acceleration due to gravity, and s is the distance, that is 90 meter. So v would be equal to, since u equal to 0, so v would be equal to square root of 2 times 9.8 meter per second multiplied by 90 meter, and that would give us a v of 42 meter per second. And how much time it needed to reach there would be given by relation v equals to u plus at. Now we know that v final velocity is 42 meter per second, so substituting this in initial velocity is 0, so acceleration is known. Now time would be equal to 42 divided by 9.8, and that would result out to be 4.3 seconds. So here velocity would be increasing from 0 to 42 meter per second, and in time interval of 4.2 seconds. So, and since the speed is going to be increasing, acceleration is constant, so the increase in speed would be a straight line, or it would be a uniform, till 4.3 second. We have assumed downward direction as positive, so initial velocity is positive, but as we are only taking care of speed, so we are only considering magnitude over here, so it is always going to be positive. So it will reach to 42 meter per second in type interval of 4.3 second, and it will be plotted like this straight line. Now we will find out the time it requires to go to a second, go upward with a reduced velocity of 0.9 times this initial velocity. So the final velocity, the velocity after impact, is going to be v2 is going to be 0.9 times 42 meter per second, and that is 37.8 meter per second. And again, acceleration of gravity is going to be 9.8 meter per second. So time interval it will take to reach zero velocity would be, since it is moving upward now, so it will reach zero velocity in some time interval, and that time interval can be calculated by using this relation. So 37.8 divided by 9.8 seconds would be equal to 3.9 seconds. So 3.9 second plus 4.3 would give us 8.2 seconds. Now this velocity will decrease to 37.8, and it will go down to 0 again in 8.2 seconds. Now again it will reach the ground level in time interval of 3.9 seconds. So, and the velocity would be again as that of the initial velocity at which it was it bounced, and that is of 37.8 meter per second. So at this level it is going to rise in again 3.9 seconds. So it would be 12.1 second. Velocity will rise to 37.8 meter per second. Now again the value will decrease to 0.9 times the initial velocity. So the final velocity is going to be equal to, after rebounding, it would be equal to 0.9 times 37.8 meter per second, and that is equals to 34.02 meter per second. So it will reduce to 34.02 meter per second. And the time interval that is required for it to become zero when it bounces upwards is equals to 34.02 divided by 9.8, and that would be equal to 3.5 seconds. Since this goes beyond 12-second mark, so we don't need to plot any further, although we can plot successive iterations with this formula, using this formula. So this explains the falling down of the ball. Question says, explain clearly with examples the distinction between magnitude of displacement sometimes called distance, over an interval of time, and total length of path covered by particle over the same time interval. And in B we have magnitude of average velocity over an interval of time and the average speed over the same interval. Average speed of particle over time interval is defined as the total path length divided by the time interval. Next we have show in both A and B that the second quantity is either greater than or equal to the first. Second quantity refers to the displacement and the path. Yeah, in this section A we have second quantity as the total distance, and in B we have second quantity as the average speed. Second quantity is either greater than or equal to the first. When is the equality sign true? For simplicity, consider one-dimensional motion only. So we need to consider one-dimensional motion, and we have to distinguish between magnitude of displacement and the distance, sometimes called distance, and the total path covered by the particle. So let's have a coordinate system which describes x and y coordinate of the path. This is the origin. So let the particle trajectory be something like this in case A, although this is two-dimensional motion. So this is one path, and the body covers up something a path like this, which is a zigzag motion from point O to point M. Now when we consider displacement, then displacement is defined as the difference in the position vector, final minus initial. So the position vector of final point would be something like this. And the initial vector is 0, so the displacement would be OM, and also it can be said that the shortest distance between the final point and initial point is termed as displacement, gives the magnitude of displacement. And displacement by the name also carries the direction, as displacement is a vector quantity. So when we talk about displacement vector OM, then it has magnitude, that is the shortest distance between O and M, and the direction, which tells us at what angle or with a reference coordinate system where the particle is, or in which direction the particle is heading. As far as the total length of the path is concerned, so the length of the part would be addition of this distance, which is a curve from point O to point M. So here we see that the distance, the length of path, is greater than the displacement or the magnitude of the displacement vector. This is always going to be true. Length is always greater than that of the displacement vector. Let us consider a one-dimensional case here now. Imagine a particle starts from this point O and it travels in a straight line. In this case, we see that displacement as well as distance, or the length of the path covered by the body, is same. So when the particle is traveling in a straight line, then the total length of the path as well as the displacement is going to be same. Now consider second case, that this will the initial point where the body starts moving, and let us assume that particle goes from O to intermediate stop N, and then it travels back to a final stop M. So the length of the path would be ON plus MN. Whereas displacement is just going to be OM. So here also we see that length of the path is greater than that of the displacement. So we can distinguish between length of the path and the magnitude of displacement, as length of the path is always greater than or equal to the magnitude of the total length of the magnitude of displacement. And also the displacement is a vector quantity and length of path is a scalar quantity. Now in B we have magnitude of average velocity over a time interval and the average speed over the time interval. We have to distinguish between magnitude of average velocity as well as the magnitude of average speed. So like here we had three cases. Here in case 1 we see that the path was little bit zigzag, and in second case we had rectilinear path, and in third case we had a path with retracted motion. So when we consider the average velocity in case 1, average velocity is defined as displacement, net displacement divided by time interval. This is also a vector quantity. So net displacement divided by time interval. Always we saw here that magnitude of displacement was less than that of the length of the path. So again here velocity is going to be less than, average velocity is going to be less than that of the average speed, where average speed is calculated as the length of the path traveled from initial to final point divided by time interval. Length of path divided by time interval. So we see that average speed is greater than the average velocity in first case. In second case we can say that since initial and final position, the magnitude of displacement, we saw that magnitude of displacement is equal to the length of the path. In this case given the same time interval, we can say that average speed is equal to average velocity. And in third case we saw that the displacement was less than that of the length of the path. So again average speed is greater than that of average velocity. Equality sign, also the question said when is the equality sign true? Equality sign is only going to be true when there is a rectilinear motion, whereas the path is a straight line. Then only the magnitude of displacement and the total length of path is going to be equal. Also average speed is going to be equal to average velocity. Thank you. The question says that a man walks on a straight road from his home to a market which is 2.5 km away with a speed of 5 km per hour. Finding the market close, he instantly turns and walk back home with a speed of 7.5 km per hour. So the question asks, what is the magnitude of average velocity and average speed of man over the time interval of 0 to 30 minutes, 0 to 50 minutes and 0 to 40 minutes. So here we see that the man is walking on a straight line, that is, the motion is in one dimension, and he goes to the market and returns back home. So let's represent this situation pictorially. Let us assume that the man home is here, O, and market is here, and the distance between home and market is 2.5 kilometers. So the first question says that magnitude of average velocity. We have to find out magnitude of average velocity. So we know that average velocity is defined as total displacement divided by total time interval. Here we see that when the man goes from home to market, he displaces by 2.5 kilometer, but when he returns from market to his home, he travels in the negative direction exactly the same amount when he traveled from home to market, that is minus 2.5 kilometer in some time interval. Now the net displacement is going to be 0, that is why average velocity is going to be 0. Now in second part of the question we have find the average speed during the time interval of 0 to 30 minutes, 0 to 50 minutes and 0 to 40 minutes. So let us take the situation 1. We have average speed in 0 to 30 minutes. So first let us find out how much time it takes to cover the distance of 2.5 kilometers, that is from when he goes for the first time from home to market. So the time required equals to distance divided by speed, which is equals to 2.5 kilometer divided by speed is 5 kilometer per hour. Now the time required is 30 minutes. So in 30 minutes he goes from home to market. Now what is the time required when he is traveling back home from the market? That is again 2.5 kilometer divided by speed 7.5 kilometer per hour, and that would be equal to 20 minutes. So when he travels from market to home, he travels it in 20 minutes. So the first part of the question asks that what is the average speed of man over the time interval of 0 to 30 minutes. So we see that in 0 to 30 minutes he is just moving from home to market, and it is given that he is traveling at a speed of 5 km per hour. So the answer of this first part is going to be 5 km per hour. Now second part says that from 0 to 50 minutes. So we see that as he turns back instantly when he sees that market is closed, so there is no time lapse between his decision making. So we can assume that the total journey is completed in 50 minutes, that is from home to market he goes in 30 minutes and instantly he turns back and travels 20 minutes to home. So the total time interval is of 50 minutes. So in 0 to 50 minutes the average speed is going to be 2 times the distance from home to market and divided by 50 minutes. So 2.5 kilometers plus 2.5 kilometer divided by 50 minutes, or we can say that 50 divided by 60 hour, which is equals to 5 multiplied by 60 divided by 50, and that will give us 6 km per hour. Now the third part of this question says that from 0 to 40 minutes. So we see that while returning back from market to home he takes 20 minutes. So and the question is asking from 0 to 40 minutes what is going to be the average speed. So 30 minutes he has taken from going from home to market, and rest remaining is of 10 minutes journey is remaining. So the 10-minute journey is going to be he's going to be at the position half of the position from market to his home, because when he is returning back from market to his home then he's taking 20 minutes. Now at the 10-minute time, he will be just in the middle of the pathway. So, and the total distance is of 2.5 kilometer, so he would have traveled 1.25 kilometer. So we can say that in 40 minutes he has traveled 2.5 kilometer plus 1.25 kilometers, and in 40 minutes, so 40 into 60, 40 divided by 60, which is equals to 3.75 kilometers divided by 40 divided by 60, which is equals to 5.625 kilometers per hour. Now there is a note. You will appreciate from this exercise why is it better to define average speed as total path length divided by time and not as magnitude of average velocity. You would not like to tell the tired man on his return that his average speed was 0. So here the comment is made when we try to mark the magnitude of average velocity to equal that of the average speed, and the question says that it gives a wrong signal, as we see in this situation when displacement is 0. Even though the displacement is 0, the man has worked and he's sweating, so it can't be said that his average speed was 0. So we see that in his whole journey his average speed was 6.6 km per hour, while his average velocity was 0. So thank you. The question says in exercise 2.9 and 2.10, we have carefully distinguished between average speed and magnitude of average velocity. No such distinction is necessary when we consider instantaneous speed and magnitude of velocity. The instantaneous speed is always equal to the magnitude of instantaneous velocity. Why? So the question is referring to exercises 2.9 and 2.10, where we found out that the average speed and average velocity of the same person going to the market and coming back was different. Average speed was of some positive magnitude, whereas average velocity was 0, as the person reached to the same position where it was initially, so the velocity was 0 as net displacement was 0. Also the question is saying that no distinction is necessary when we consider instantaneous speed and magnitude of velocity. So here we have to clarify the difference between average versus instantaneous values of speed and velocity. So let us look at the definition first of all. So we have average velocity described as net displacement divided by time interval, whereas instantaneous velocity is described in very short average velocity is described as net displacement over time, whereas instantaneous velocity is described over very small time interval and thereby very small displacement, which is equivalent to the length of the path traveled, and the length of path over time is average speed. Thus we can say that for a very small interval of time, the displacement magnitude is equal to path length. Thus, no distinction is necessary when we term average speed, the instantaneous speed, as a magnitude of velocity. Thus, no distinction is necessary when we consider instantaneous speed and magnitude velocity. Also, the magnitude of velocity is equal to, also the magnitude of instantaneous velocity is equals to that of instantaneous speed for a very small interval of time. Thank you. In this question, we have look at the graphs A to D carefully and state with reasons which of these cannot possibly represent one-dimensional motion of a particle. So we have been given 4 different graphs A, B, C and D, and in which we have to find out which of these possibly cannot represent one-dimensional motion of a particle, and also we have to give reason for the same. So the graph 1 is position time graph, in which we see that at the same point of time, if we draw vertical on the time axis, we see there are 2 different positions at the same point of time. So this is very unrealistic and it can't be true. So this graph cannot represent the one-dimensional motion of a particle. And the similar type of situation is seen in figure B also, in which a velocity time graph is given at the same point of time, like here, when we draw vertical over the time axis, we see that at the same point of time we have 2 different velocities, which is very unrealistic. In graph 3, you see we have a speed time plot, and in this plot we see that speed has decreased from 0, that is, it has gone negative, which is again unrealistic and it can't be true. Speed is never less than 0, as speed is equal to length of path divided by time interval, and length of path cannot be less than 0, so speed cannot be less than 0. And in 4, that is D plot, we have total length versus time plot, and here again we see that at this instant of time, total length of path has decreased with time. This is again untrue, because even though when you trace back from the position, like you have started from A, reached position M, and you are again retracing your position back, even if you have reached here, then the displacement might be of this magnitude, but the path will be like this. So the path is going to be OM plus MN. So path cannot decrease with time, so this graph is also unrealistic. Thank you. Question says that figure 2.11 shows xt plot of a one-dimensional motion of a particle. Is it correct to say from the graph that the particle moves in a straight line for t less than 0 and on a parabolic path for t greater than 0? If not, suggest a suitable physical context for this graph. So the question is trying to infer that does xt plot represents the trajectory of the path that the particle follows in a one-dimensional motion? The answer is no. Xt plot does not represent the trajectory of the path. So the time less than 0, the time axis, since it is 0 in the position scale, it represents that the particle was at rest, and it does not represent that the particle moves in a straight line for t less than 0. Instead, it was at rest. So the particle was at rest at t less than 0, and for the time t greater than 0, we see a parabolic rise in the position of the particle with respect to time. So let's now find out the context of this motion. The position varies. Mathematically, we can say that the position, that is x, is directly proportional to the square of the time axis, and substituting here with a proportionality constant, position of the particle may be written as kt square, where k being the constant of proportionality. Now, if we try to correlate it with a similar motion of particle, the equation of a motion of a particle, that is s equals to ut plus half at square, and if we substitute u, that is the initial velocity, with 0, then the equation of motion in the given problem is very much equals to the equation of motion that we have for motion under constant acceleration. This will, after substituting u equals to 0, this will come out to be s equals to half at square, where this half a is constant, which may be substituted for k. Now, this constant motion under constant acceleration, if we try to find out an example for this, the perfect example where u is 0 and the particle is traveling under constant acceleration is when ball is dropped from a certain height. Let's say that h height. When the ball is dropped without any initial velocity, u equals to 0, then the motion of the particle is under constant acceleration, and it varies with this. The position can be computed with this equation. So we can say that the context representing the graph is trying to represent the context of a ball falling with the initial velocity of 0, and also the position coordinate is taken 0 over here, and x direction, positive x direction, is assumed in the downward direction of the ball. That's why it is 0 over here, and it is rising as the time progresses. So x is positive in this downward direction. Thank you. The question says, a police van moving on a high speed highway with a speed of 30 km per hour fires a bullet at a thief's car speeding away in the same direction with the speed of 192 km per hour. If the muzzle speed of bullet is 150 meter per second, with what speed does the bullet hit the thief's car? Here, muzzle speed refers to the speed of the bullet as it comes out from the gun. Let's assume that this is the gun and the bullet is coming out from here. Now the speed in relative reference to this gun, the pipe of the gun is known as, the barrel of the gun is known as the muzzle speed. So this speed is 192 km. This speed is 150 meter per second. Now let us pictorially represent this question. So we have road, we have a police car, we have a thief's car, police car is going at a speed of 30 km per hour, and this thief's car is going in the same direction, the speed of 192 km per hour. Now bullet is fired at a speed of 150 meter per second. So the question asks, with what speed does the bullet hit the thief's car? So the question is asking, like, at what speed does thief's car get hit by the bullet? So we see here that the unit of velocity it's different, so it can't be compared. So let us first convert this kilometer per hour into meter per second. So upon calculation, like 30 kilometer per hour can be written as 30 into 1000 divided by 3600 meter per second. This will come out to be 8.33 meter per second. And similarly, 192 into 1000 divided by 3600 meter per second will come out to be 53.33 meter per second. So this is going to be 8.33 meter per second. This is going to be 53.33 meter per second. Now it says that the velocity of this bullet with reference to the police car is 150 meter per second. It means the absolute velocity with reference to this road is going to be velocity of bullet with reference of road. Our actual velocity is going to be 150 meter per second. meter per second plus 8.33 meter per second. Since the gun is also traveling with the police, so the velocity will add up to 158 meter per second, roughly rounding it up. Now the velocity of the thief's car is 53 meter per second, so the thief car will be hit by the velocity difference, that is 158 meter per second minus of 53 meter per second, that will come out to be 105 meter per second. So this is the velocity by which the thief's car will be hit by the bullet. Thank you. The question says, suggest a suitable physical situation for each of the following graphs. There are 3 graphs and we have to suggest a suitable physical situation which will lead to these plots. So the first is position time plot. So here we see that up to some specific point the body is at position 0, it means the body is at rest, and then it moves with a constant velocity. The straight line shows that the velocity was constant because the tangent to this line will be constant. And then in part B of the graph we see that the velocity is decreasing and the position is somewhat negative, and then again the particle comes to rest. So if we try to find out the physical situation for which this graph is valid, then we can think of a ball. Let us assume this is the particle. When the ball is kicked with a constant velocity, it will move like this. Let us consider the positive x direction to be this axis. So at first the ball moves with a positive velocity in this direction, then it will, so this line, when the ball approaches the wall, is represented by a part of the graph. Now the ball reaches here, and then now we see that the position is decreasing. So again the ball will rebound like this, and it will reach here. This is the point where the position, the blue line or the particle, the blue line will cut the time axis, that is the 0 position. The ball reaches here. Now the ball moves further in the negative x direction, and it reaches somewhat here and then stops. So there may be another wall or some obstacle which will lead to stopping of the ball. So this is the point where it becomes, where its velocity reduces to 0, or it becomes static for further time. So the this can be represented, the physical situation leading to this graph can be represented by a ball which is strike a wall and then rebounds and then strike another ball and then finally becomes to stop. Now in graph B we see that it is a velocity time plot. Velocity, the plot starts with a certain velocity and then it reaches to 0, and then it goes to some negative velocity of this approximately the same magnitude, and again it starts with a positive velocity and then again it becomes to 0, and then again it goes to some negative velocity. So this can be assumed, and this can be thought of a situation like this. Let us take the positive x direction to be above. Now when we throw a ball with some with some initial velocity, let's say u, then initially the ball is having a positive velocity. It reaches some highest point with velocity being 0. Now at this point the velocity is 0. Now again the velocity starts increasing in the negative direction, so the velocity becomes negative, and then the ball comes to the same initial position with the same magnitude but with a negative sign or a negative direction. Now again the ball will rebound from the ground, losing some of the velocity. It will again go to a full stop at some highest point and then will again come back. So this graph is representing this velocity only. So this point is when the ball is thrown upward, and this point is when it cuts the origin. It's the point when the ball reaches the first time its highest position and then it becomes negative. It means the ball has come down at the initial position of the start. Now again it rebounds with some decay in velocity as it will go upward, so its velocity is again positive. So this is the point where it rebounds, and then this continues until the velocity decays. So now we see the third plot. We see the third plot as the acceleration is 0 at until certain point of time, and then it suddenly shoots up and then it goes down immediately. So in certain situation, the thing is that this can be explained by sudden change in velocity in a short interval of time. So we can think of a situation like when like this is 0 acceleration. It means it represents constant velocity. A ball is approaching some obstacle at a constant velocity and it rebounds very quickly. So in the physical situation nearby around us can be thought of a cricket ball match where a ball is hit by a bat and it rebounds and it goes and just changes its velocity from one direction to just opposite direction or some other direction. So in that case the acceleration shoots up to a very high value. So the physical situation for this plot may be thought of a cricket ball rebounding. Thank you. The question says that figure 2.13 gives the xt plot of a particle executing one-dimensional simple harmonic motion. You will learn about this motion in detail in chapter number 13. Give the sign of position, velocity, acceleration variables at particle at time t equals to 0.3, 1.2 and minus 1.2 seconds. So we have to give the sign of position, velocity and acceleration at time t equals to 0.3 seconds, 1.2 second and minus 1.2 seconds. So at first let us know a little bit about one-dimensional simple harmonic motion. So simple harmonic motion is a type of motion in which there is a equilibrium point and a body or a particle swings about this equilibrium point. So it will go at first here, then it will come back here with the same distance xx. So this is equilibrium point because at this point of time there is no acceleration acting on the body and it has a maximum velocity, and at this point of at this position, when the body is at this position, let us say position 1 and position 2 and position 3, at this position the velocity is going to be 0 and acceleration is acting in the negative direction. If we take this as the positive direction, then the acceleration, so from point 2 to point 1, when the particle travels from point 2 to point 1, it decreases its velocity. As I said before, at point 2 the velocity is maximum, and as soon as it reaches point 1 its velocity decreases to 0. So when it travels from 2 to 1 its velocity decreases, so acceleration is negative when it is moving away from the equilibrium point. Now when it moves towards when it goes from 2 to 1, acceleration is negative. Now when it moves towards the equilibrium point, then its velocity is increasing or its acceleration is positive. And as soon as it passes the equilibrium point to go in this direction, again the acceleration is going to be opposite, in the opposite direction, that is in this direction. So this time the velocity is in negative direction and the acceleration is in positive direction. So this keeps on happening. Now the same is represented in this graph, as it says that it is executing a one-dimensional simple harmonic motion. So let us see the points of the three main points in this motion. Let us point out it in the graph. The equilibrium point is where the position coordinate is 0. So these are the equilibrium points. At these points the acceleration is going to be 0, as we discussed right now. And at the extreme points the acceleration is in the opposite direction of initial body movement. So when we consider this as the extreme point, then the body was moving in the negative x direction, so its acceleration is going to be positive. So this point may be represented by this third coordinate where x is negative. So while body is here, we can say that when the body is going from equilibrium position to its negative extreme position, then we can say that the acceleration is acting in the positive x direction. So acceleration will be positive in this point. So we have a question where it at time 0.3 seconds. So this would be somewhat 0.5 second and 0.3 second would be here. So this is the extreme negative point, and so the acceleration is going to be in the positive direction. So acceleration is going to be positive. Now velocity, since it is moving in the negative x direction, so its velocity is already going to be negative. And since it is in the negative x direction, so position is also going to be negative. Now let us consider point 1.2. So this point would be 1.5. So 1.2 would be here. Now the body is traveling from its equilibrium position to its extreme positive side. So the body is traveling from 2 to 1. So when the body is traveling from 2 to 1, its acceleration would be in the negative direction, because it is inhibiting, which will lead to zero velocity at this point of time. So we can say that its acceleration is negative direction at second 1.2. Since it is traveling in the positive x direction, so its velocity is going to be positive, and since it is above the graph of time t, so it is going to be positive. Position is also going to be positive. Now consider the third case where it is minus 1.2 seconds. So this is going to be minus 1.5 and minus 1.2 would be here. So we see here that the body from negative x direction, the negative extreme point, it is moving towards zero equilibrium position. In this part of the graph, we see that from point 3 to point 2 movement is there of the particle. So while it is moving to point 2 or the equilibrium position, its velocity is increasing and its acceleration is in positive x direction, because the body has recovered from zero velocity to, and now the acceleration is acting in the positive x direction, which will lead to increase in velocity. So the velocity will be positive. The velocity is going to be in this direction, that is the positive x direction, so it's going to be positive. Acceleration is also going to be positive. Now position is negative because it is in the negative x direction. Thank you. The question says that figure 2.14 gives xt plot of a particle in one-dimensional motion. 3 different equal intervals of time are shown, that is 1, 2 and 3. In which interval is the average speed greatest and in which it is the least? So we have to talk about average speed, and also we have to talk about the sign of average velocity. In 1, 2 and 3 time intervals. So we have to find out which has the average velocity that is the greatest in magnitude. So we see here that in xt plot, the tangent to the curve gives velocity. Also, since it is a time interval, we can say that the average of this tangent over this region will give us the average velocity, average speed. Now when we plot the tangent like this, so let us plot the graph again over here. So it is something like this. So the tangent at interval 1 is going to be like this. Tangent at interval 2 is going to be something like this, and tangent at interval 3 is going to be like this. So considering the magnitude of the tangents, irrespective of the sign, as we are dealing with average speed in this case, so the magnitude of tangent is greatest in 3. That is why the average speed is of 3. Third time interval is going to be the greatest. So average speed of interval 3 is greatest. And Now the average velocity sign. So the tangent sign gives the average velocity sign. So in the first interval it is positive as it is acute angle, and in second interval it is 0, so it is going to be positive as it is subtending a 0 angle. So, and in third it is obtuse angle, so it is going to be negative. Thank you. The question says, figure 2.15 gives the speed time graph of a particle in motion along a constant direction. The three equal intervals of time are shown. In which interval is the average speed greatest? In which interval is the average acceleration greatest in magnitude? In which interval is the average speed greatest? Now, the second part of the question is, choose the positive direction as the constant direction of motion. So let us first cover these two questions. Which interval average acceleration is greatest in magnitude and average speed is greatest in magnitude? So average acceleration in a speed time graph can be plotted using can be found out using finding the slope in the three intervals, average slope. So slope at interval 1 is going to be something like this, and interval 2 is like this, interval 3 is like this. So as far as the magnitude is considered, the interval 2 has the greatest slope, that's why the greatest magnitude or the greatest acceleration. So in the second interval the acceleration is greatest, and average speed, as far as average is, in which interval is the average speed greatest. So since it is a speed time plot, we can easily find out the average speed, which one is greatest. So interval 3 has the highest point, so it has to be the interval of highest speed. So we can say that the highest speed average is going to be in the third interval. Now the third part of the question is choosing the positive direction as the constant direction of motion. So it is saying that since it is a one constant particle is moving in a constant direction, and that direction is going to be positive, give the sign of v and a in three intervals. So we have to give the sign of velocity and acceleration in all the three intervals: interval 1, 2 and 3, and v and a. So let's talk about interval. So in this case, as it is clearly mentioned that the particle is moving in the positive direction and the direction is constant, so the velocity in all the three intervals is going to be positive. So we should simply say that velocity is going to be positive in all the three intervals. Now as far as acceleration is considered, this slope gives the direction of acceleration, and we see that 1 and 3 are the acute angles, that's why the slope is going to be positive in interval 1 and 3. So we can say that acceleration is positive in interval 1 and 3, and second interval has obtuse angle, that's why its acceleration is going to be negative. Also we have to find out the acceleration at points A, B and C and D. So again, the acceleration can be found out using the slope, and so let us find out again the acceleration at A, B, C and D. So when we plot the slope at graph at point A, it is going to be a horizontal line, so acceleration is going to be 0, and at B also it is going to be horizontal line, so it is going to be 0, and acceleration at point C is also going to be 0, and acceleration at point D is also going to be 0. So since all these 3 points, The tangent is simply a horizontal line that is zero angle, subtending a zero angle with the horizontal. That's why its slope is going to be 0, or the slope of speed time graph is going to be 0, or the average acceleration is going to be 0. That's it. Thank you.